In this video, we would like to discuss dynamic programming. We want to use longest common subsequence as example to give further discussion. Dynamic programming is a powerful algorithm design technique that has been widely used to solve problems, specifically optimization problems. Dynamic programming look very like divide and conquer method, right? Solves problems by combining the solution to sub-problems. And either method, we use recursion. Either method, we take a look at the whole problem, we cut into the sub-problem. We check what is the structure of this problem. And then based on the sub-problem relationship, we divide into different technique. We use different technique. If the sub-problems are adjacent, and if the sub-problems are disjointed, in that case, we want to use divide and conquer. If sub-problems, they do have overlaps, in that case, we want to reuse the results from the previous sub-problem solution. And in that case, we have to save the sub-problem solution somewhere. Usually we call dynamic table. It's an array. Multi-dimensional array could be. And then in that case, the later calculation can use the previous calculation, right? And here in this table, we want to show you, we want to visualize the big difference between divide and conquer and dynamic programming. First, we take a look at the first two rows. And in these two rows, we can see here, this is the common features. Both use recursive ledger, and both view the problem as a connection for sub-problems. But the difference is divide and conquer, we have independent sub-problem. Dynamic program, we use overlapping sub-problems. And dynamic programming, primarily for optimization problems. We could have optimal substructures corresponding to optimal solution to problem contains with it optimal solution to its sub-problems. When developing a dynamic programming algorithm, we follow a sequence of 4 steps. First, characterize the structure of an optimal solution, which corresponding to, we would like to take a look with the optimal solution to a problem contain the results of optimal solution to this sub-problem. This is the first step. We need to find out this structure in the specific problem, or else we cannot use that. The second step, we have to define the recursive function. We want to recursively define the value of an optimal solution. The third step, we have to compute the value of optimal solution, typically in bottom-up fashion. In this corresponding to, we need to save these results in the dynamic table. We fill this table from the bottom to the top. This we call bottom-up fashion. The first step, construct the optimal solution from computed information. We got the optimal results, and then we have to construct the solution for the user. Just like a road cutting problem, we tell other people, the user, what could be best profit. Then we also have to tell them what is specific cut, where to cut, where you will get the best profit, right? Okay. In this lecture, we would like to use longest common subsequence as the example. It do have very wide applications. And one of the specific application corresponding to sequence alignment, let's see here, we give a sequence, right? DNA strands and consist of a sequence of 4 unions ACGT. And then each DNA sequence consists of a number of these 4 unions. For example, S1 sequence corresponding to ACCG, GTCG, S2 corresponding to GTCG. When we have some time, they ask us, we want to check how this How similar is this two sequence corresponding to? Now, these have a specific usage. For example, this DNA sequence corresponding to one of the species, and sequence 2 corresponding to another species. People want to check the evolution distance between two species. In that case, it corresponding to sequence alignment, also corresponding to find the longest string S3 containing bases that also appear in S1 and S2. And also make sure they follow the same order. Find the common sequence GTC, GTC, GG appear in sequence 1 and also appear sequence 2. They may not be adjacent. Each base may not be specific adjacent in each sequence, but the order is the same. Let's formulate as the computational problem. Let's say sequence Z, which is a common sequence, longest common sequence Z, Z1, Z2, ZK, is a subsequence of X, X1, X2, Xm, if exists I1, I2, Ik, such that we have, for any j, we have Xij equal to Zj. And what corresponding to, if we give a sequence X, the subsequence Z, all elements of Z came from X, and also make sure they are in the same order. And we use this J to represent, we use this Xj corresponding to we use this Ij, J from 1 through K corresponding to what we find out the elements in specific order. For example, Z equal to BCDB is a subsequence of XABCD DAB with index sequence 2, 3, 5, 7. So this is the index sequence. They should be in increasing order. Z is a common subsequence of X and Y if Z is a subsequence of both X and Y. For example, X equal to ABCB, Y equal to BDCB. The common subsequence could be BCA, right? BCA. BC, either one, A, right? So we need to make sure what we have the index, what we retrieve this subsequence, the index is in the increasing order. But this BCA is not the longest one, because we could find BCBA even longer than that. The longest common subsequence problem corresponding to given two sequences X and Y, find the maximum length common subsequence Z. Within the 4 steps, right? The first step, we have to characterize a longest common subsequence with the solution for this sequence contain the optimal solution of its subproblems, and we say that's true. Given sequence X and Y, for any longest common sequence Z of X and Y, they could have 3 possibilities. First, Xm equal to Yn. And in that case, it is we say Zk could be equal to Xm or Xy, right? And then if that is true, then the Zk minus 1 is a longest common sequence of Xm minus 1 and Ym minus 1. If we draw the picture, let's say we have X. Let's use array to represent that. We have Y. We use array to represent that, right? we see this is x, this is x1, x2, and this is xm, this is y1, y2, and this is the yn, right? We see if that is true, if it happens, okay, I think it doesn't save. Okay, so if happen xm and yn, they are equal, in that case it is what we form z, we want to find the z, right? So z, if this is happen, then in that case we want to use the results of, because this is make a contribution, right? So this should be xm or yn, right? Then in that case it is, if we take this contribution, the remaining, what we have remaining here, from x1 to xm minus 1, yn minus 1, suppose we'll make this part, right? Combine these two, we make this one. So this is what corresponds to the first condition, xm equal to yn, zk equal to my, right? Then in that case, the zk minus 1 is the longest common sequence of xm and ym minus 1. Corresponding to the length of m minus 1, length of n minus 1. If xm not equal to yn, in that case, if that's not equal, then in that case we may consider which one will contribute to the longest common sequence. If we say maybe no, y will make contribution, or we say okay, we are sure xm will not make the contribution. If we know xm will not make a contribution, we say z, the longest common sequence, came from the previous x1 through xm minus 1. Line this subsequence with the whole y, right? This is one condition. Second condition, if xm not equal to yn, definitely both cannot contribute. And we are sure yn will not contribute. Then in that case, the longest sequence came from x, the whole x, with one smaller y, right? To prove that, we say if, for the first case, they have two conditions, and we say if zk not equal to xm, if this is not happen, if they are not the same, but happen zk not equal to xm, and we wanted to use xm to contribute, and appending xm to z contradicts the longest lecture of z, right? Because you what is longest one? The zk minus 1 is longest one. You add one more there, it's not longest anymore. To establish longest lecture of zk minus 1, suppose common sequence w of x minus 1 and y minus 1 has length larger than k minus 1. Appending xm to w, generate a common subsequence of length greater than or equal to k, which is contradictory to what we have, the longest common sequence. Take a look at the second condition. Comma subsequence W of x m minus 1 and y of length larger than k would also be comma subsequence of x m y, contradicting longest lecture of z. And then, based on what we observe, the optimal solution, the optimal structure of this computational problem, and we can try to write down the recursive solution. And we say we check the last element in two sequence if they are same or not the same. If the same, we find the longest comma sequence x m minus 1 y m minus 1 plus what we have the last guy, right? In that case, it is, we see the last element in both sequence made the contribution. If this is not the condition not satisfied, then in that case, we go to the red branch. And in the red branch, we'll have to find out which one, give the, which xm or yn, which one will make the contribution, and which one the contribution will finally increase the longest the sequence length, find the common sequence length. We use maximum from the longest sequence x minus 1 with the whole y, or the longest subsequence whole x with the y and n minus 1. So this we are sure the yn will not be equal to zk. And this one corresponding to we are sure xm will not equal to zk. And such that we can write the recursive function. We say when x equal to 0 or j equal to 0, let's see here, when we find out overlap subsequence, because when we have to calculate the longest common sequence x and y, we have to check what is subsequence of xm minus 1, yn minus 1, right? Which is belong to LCS xm minus 1 y, and also belong to LCS xm yn minus 1. So this is an overlapping problem structure. In that case, definitely we want to use dynamic programming. And we write down recurrence for length of optimal solution. And we use Cij corresponding to the length of longest common sequence of xi and yj, right? So, for example, we have x, which is equal to the m, right? We have yn. Here we use x to represent what is x is yj, right? To represent this subsequence. And is equal to if x and I equal to 0 or j equal to 0, which corresponding to the subsequence is long. In that case, there's no any comma sequence, right? One is empty, so it's 0. So if I and j larger than 0 and xi equal to yj, in that case, Cij is equal to Ci minus 1, j minus 1 plus 1. We count the contribution of the last pair. And then the longest sequence, the length is, compared to what we have before, it is Ci minus 1, j minus 1 plus 1. If it happen xi not equal to yj, if they are not equal. If they are not equal, we pick up the maximum one, right? It's the length. Let's take a look at example. Comparison of two DNA sequence. And we use x to represent the first one, y to represent the second one. The brute force method can compare each subsequence of x with the symbols in y. From given x and y, we first find out which one has longer sequence. We say x is longer, right? Y is shorter. And in such case, we want to find all the subsequence. Let's see, we list Let's write it down here. So this is corresponding to, if we given x and y, to find longest sequence of x and y, right? And we want to use, first let's check brute force method. So first we check the longest sequence. Step 1, the compelled length and y, right? We do the comparison and pick up the smallest one as the what we have. Step 2, find all subsequence of longer sequence. In this case, x is longer, and they have 7 letters. So find all the subsequence. We have Cn. We have what? It's exponential actually. How many sequence we have? So we see that we pick up nothing. Pick up 1 plus pick up 2 plus pick up all. So in that case, we have 2 to the power of n subsequence. And in that case, you can imagine step 3, align the short sequence with each subsequence in step 2. And so we see from here, we see the total runtime is what? Is O m to the power of n, right? Can you see that? So this is the brute force method, which definitely gives us exponential and solution, and which is not efficient. And let's take a look dynamic programming solution. First, we'll find the length of a longest comma sequence. Later, we will modify the algorithm to find the longest comma sequence itself. Define xy, xi, and yj to be the prefix of x and y of length I and j respectively. Define Cij to be the length of LCS of xi and yj. Then the length of longest comma sequence of x and y will be Cmn. So this is what we have the recursive relation. Now, based on what we discussed here, we see we can start x, I, and j equal to 0. And we need to define, since we have we have received the results for the previous sub-problem, the previous solution, right? And in that case, with the sub-problem, we have received the results. So in that case, we need to have dynamic table. What is the dimension of this dynamic table? We say it should be 2 dimension. And then we have to check the base case. I equal to 0, y equal to 0. And we initialize to be 0. And all the rows, the columns in the first row and the first column should be 0. And then after that, we started to calculate Cij. We consider 2 cases. In the first case, xi equal to yj. And the second one, xi is not equal to yj. If it's equal to xi equal to yj, in that case, one more symbol in strings x and yj matches. So the length of longest comma sequence xi and yj equals to the length of longest sequence of a small string xi minus 1 and yi minus 1 plus 1. And if it happens xi not equal to yj, or symbols do not match, or solution is not improved, the length of LCS xi and yj is the same as before. And question 1, not just take the length of LCS xi minus 1, yj minus 1. The reason it is we have to consider, maybe you will count the one of the element and compare this element with some other element in the second sequence. This is the algorithm for the longest common sequence dynamic program-based solution. And first we check the length and for x and y. In such case, we can initialize the dynamic table and also initialize the first row and first column to be 0. And then after that, it is we fill in this dynamic table from the lower index I and lower index j. And we focus on this recursive solution based on two conditions, xi equal to yj or is not. So if it's the same, then we check ci minus 1, j minus 1, and plus 1. What else we pick up from one of cases. And then now let's take a look at this example. So we have A, B, C, D. We have we have A, B, C, D. We have to align this x with this y, and then here we see this could be the result. Let's take a look to see how to fill the table. First, we needed to have a two-dimension table, and this is the 5 times 6 array, and each row here, you can see this is the row name and this is the column's name. Row names corresponding to what we have the X sequence, and the columns here corresponding to the Y sequence. And when we fill this table, it corresponding to what is solution, what is optimal solution for the subsequence xi and yj, right? So first, we initialize first row and first column to be 0. The reason it is, if index I or j is equal to 0, it means one of the sequence is long, is empty. In that case, of course, no results. Then after that, we pick up the first element from each side. Let's say from this side, right? We check for A in the X sequence, and we compare this A with this B. If it's the same, then we say we counted plus 1 based on the previous results with plus 1, right? In this case, A and B not same, and then we pick up maximum 1 from this side or this side, right? It corresponding to, maybe if you choose this side, it corresponding to you map the whole xi with the yj minus 1, right? If you choose this side, it corresponding to choose the whole y but xi minus 1. In this case, it should be 0. Then you compare the net elements in the yj, and so you meet the another a. Then in that case, so since this is we count this matching, and then you have this number plus 1. Then you continue to check for the last element. So this is consider subsequence of xi which hold for one element. Align this subsequence with each or the possible subsequence in the y. And then after that, we check. Then after that, we check we expand the subsequence of xi, and we have AB. Now we check AB, map AB with the with the adjacent subsequences, and we map this B is mapped here, right? And this is found one match, and then we continue. So when you continue here, you see since you already have one match, you always remember what you have this one match until you meet another match guy, right? Then this is for the subsequence AB. Now you count for ABC in the X. You follow the same thing. Okay. Then the last step for this is corresponding to the whole sequence X compared with the whole sequence B. And in that case, we found this is the maximum number, and it's also corresponding to the length of longest common sequences. And after that, we have to think about, we need to find the actual longest sequence. You can just know this number 3 is not enough. We have to find out the common sequences. And then what we do is we trace back, and to check, well, the count, this match has have the contribution, the number of match has been increased. We trace back to find out this, and then we trace back, we find out this is different from is previous this one plus 1. You count this one, right? Then you continue. Because here you cannot use this one, you have to go back to here and check what is increased here. And go back to here, check what's increased here. So this is what you picked up. BCB, right? Okay. So in this one, we use this example to talk about how do you find the optimal structure of the computational problem. And how can you write down the recursive relation, and how can you fill up the dynamic table, and the last step we have to trace back to build the final results, final solution. Okay, see, this is also give you the algorithm for the last slides, give you the solution, how do you trace back. I think that's it.